Hi, and welcome to the second lesson on the mechanics of connected particles. The first thing that I want to do is just really highlight the key method when looking at force problems within mechanics. If you follow these three steps, typically you'll be able to answer almost any question. So the first and the most important step is to really read and understand the problem. You might have to read it 2 or 3 times to really get it. And the aim here is to translate that information, the paragraph, into some sort of diagram. If you can summarize a whole lot of information in a diagram, it will just help it to sit in your mind a lot more easily, and you'll be able to work with the numbers without having to keep rereading it. Secondly, once you've got a diagram that sort of summarizes the whole situation with all the numbers, the key information, what you want to do then is draw a separate diagram for each object. Okay, this will then help you to apply F equals ma to each object and solve. Basically, then you end up with a pair of simultaneous equations that you can solve simultaneously. Most problems can be solved using that 3-step method. Sometimes there is a quicker method, but this one, whether the problem is easy or hard, will always work. And I just want to encourage you to do this, or at least get confident with this, so that if you see a quicker method, you can use it, but if you don't, you can always fall back on this. Finally, sometimes you might then need to apply constant acceleration formulae to take the problem a little bit further, but typically the first 3 steps are enough. So we're going to look at today the normal reaction force, often called the contact force. The word normal here means perpendicular, not ordinary, but 90 degrees to the surface. And it's experienced by any 2 objects that are in contact with one another. So here, if we have a box sitting on a floor or a table, then the box will experience the normal reaction. We typically give that the letter R because N means our units, newtons, so R newtons. And that is always going to be 90 degrees to the surface of the table. So here, if we've got a box sliding down an inclined plane, then the reaction force is now out in that direction, 90 degrees to the surface. You get the idea. Okay, this one over here, pointing out 90 degrees perpendicular to the surface. When it's a curved surface like this one, we basically take the tangent, and it's 90 degrees to that tangent. Okay, so there's the tangent, and it's 90 degrees to that. And typically, there'll be one flat surface. And as you can see here, it's perpendicular to that flat surface. But typically, it's perpendicular to the tangent of the point of contact. And so here, the man pushing against the wall, stick man pushing against the wall, and will experience a normal reaction here off the wall, perpendicular to that. And then also, let's label that R1, a normal reaction here and a normal reaction here, anywhere that is in contact. So we might call that R2 and R3. Okay. There may be other forces going on. For example, friction might be acting to stop his feet from slipping. So we might find we've got friction here, but at the moment we're not modeling friction. We're just keeping it as a one-dimensional problem. So key point here, the normal reaction, the contact force, the normal reaction, any 2 objects in contact will experience it, and it is always perpendicular to the surface. Because the normal reaction comes from the contact, it's this force that gives us the application of Newton's 3rd law. Every action has an equal and opposite reaction, or every force has an equal and opposite force in the other direction. So we're going to be using this normal reaction to model problems under different accelerations. Let's have a look at this example here. Forgive the R's all over the place. You'll see why they're there in a moment. So we're going to look at a person standing in a lift. They've got a mass of 76 kilograms, and we've got to find the magnitude of the normal reaction exerted by the floor of the lift on the person when the lift is not moving. We'll start there. So we're interested in the normal reaction experienced by the person. Okay, so on the person. So here's my diagram that kind of represents the whole situation. Person in the lift, cable of the lift pulling it up. And in a minute, it's just not moving. So I'm going to redraw this diagram. Okay, and I can't be bothered to draw a person. I'm just going to draw a box. That's my person. Okay, and I'm going to label all the possible forces. Firstly, the weight. That person will feel their own weight. So this time 76 times the force, acceleration due to gravity, and it will be that many newtons. But they'll also experience the normal reaction from the floor of the lift, and it's not moving. So I'm going to choose my positive direction to be upwards. Okay, and we're just going to apply F equals ma. So the forces, we now need to substitute these forces into here. You need to write them all down. Don't add them together yet. You can actually get a mark for just substituting all the possible forces. So positive is upwards, so we're going to say R is positive. We're going to have minus 76 times G acting downwards, and that's going to equal the mass 76 times the acceleration, which is 0. Okay. So in this case, we're going to get R minus 76G equals 0. So R just equals 76G. If G is equal to 9.8 meters per second squared, we get 744.8 newtons. Now, because G is 9.8, it's only accurate to 2 significant figures. We don't know its accuracy to 4 significant figures. So we have to round this answer. If we give this answer here, we're saying we know it to be this exact value, or this value to this accuracy, but we don't. So we're claiming more accuracy than we know. So we have to actually round that to 740 newtons to 2 significant figures. That's really important because it shows that there is an element of error in my answer. And if anybody wants to use my answer and they need it more accurate than that, they know that they can't trust my answer because I haven't included enough accuracy within the force of gravity. Those of you doing physics will be probably familiar with this concept. So here we note that the reaction force is basically equal in magnitude to the weight. But that's only because they're not moving. They're in equilibrium. If they're in equilibrium, then the forces have to be balanced so that, because of Newton's second law, if we're going to have acceleration equal to 0, then the forces have to be 0. So that's why these things are equaling 0, or rather equal to each other but opposite in direction. Don't get confused or start thinking that the reaction is always opposite and equal to the weight. That's not true. And we're going to see that now in each of these cases. So here we're going to look at exactly the same problem, but now the person's going to be moving up with an acceleration of 2.6 meters per second squared, and then down with 2 meters per second squared, and then moving down with a deceleration of 2.6 meters per second squared. So we're going to have a look at each of these 3 cases. The diagram is basically the same with one exception. So this time the person is moving up. Okay, so here's my acceleration. A equals 2.6 meters per second squared. So they're moving up and they're accelerating up. So obviously upwards is going to be my positive direction, and so we'll apply F equals ma, and we'll see what happens to the normal reaction here. So F equals ma, we're going to have the same equation as before, R minus 76G equals mass, which is 76, times acceleration, which is 2.6 meters per second squared. So if we rearrange this, we're going to get R equals 76G plus 76 times 2.6. And if we add those together, type it in your calculator, you get 942.4 newtons. Again, we have to round it. We've got gravity to two significant figures over here, so we're going to have to round this to 940 newtons to two significant figures. Okay, so notice here that the normal reaction was 740, but now it's 940. Why? Because the reaction is not only just supporting, the normal reaction is not just supporting the weight of the person in equilibrium. Here, the reaction force is having to support the weight of the person and accelerate that person up at 2.6 meters per second squared. So it needs to be bigger. And so here we can see the reaction and the weight, they're not equal in magnitude, they are different. Let's keep going. F equals ma. Actually, I would encourage you now to pause and have a go at the next two questions for yourself. See if you can do them. I'm going to run through them now. Pause the video, have a go. So now we're told that it's moving down with acceleration of 2.6 meters per second squared. So downwards and moving downwards and accelerating downwards. So here, I'm going to take downwards as my positive direction. And so we're going to take 76G minus the normal reaction equals 76 times 2.6. Rearrange this to get the normal reaction, that's what we're interested in. So 76G minus 76 times 2.6 equals positive R. Plug that into your calculator and you get R equals 547.2 newtons. Again, round it to 550 newtons. Okay, and so you can see this time the reaction is less. Well, why is that? Well, here, because it's accelerating downwards, the reaction is not having to support the whole weight of the person. Part of the weight, the force of weight on that person, is accelerating this person down by 2.6 meters per second squared. And so the reaction, the normal reaction force, is only having to counter the rest of the weight as this person accelerates downwards. Finally, we are moving downwards, so I'm going to take downwards as my positive direction, but we are decelerating. So acceleration is now negative 2.6 meters per second squared. So again, F equals ma, same equation as before, 76G minus R equals, but this time 76 times minus 2.5. And so here we're going to rearrange to get R as 76G plus 76 times 2.5. So this time the negative I've added it to both sides. As I move it to the other side of the equal sign, that's going to give me R. Type that into your calculator, and you're going to get 942.4 newtons. R equals 940 newtons to two significant figures. And you'll notice here that that's the same as this first one here. So moving up with an acceleration of 2.6 meters per second squared is the same as moving down and decelerating with 2.6 meters per second squared. It's worth just making sure that you understand that. Please note here, some of the most important parts is drawing the diagram and then being careful to take into account the negatives. Like, in which way are you moving? Choose your positive direction. And which way is the acceleration? Is it positive or negative? And again, the forces are they positive or negative. Get that right, and the rest is just algebra. So to kind of build on the skill of being able to draw diagrams for these things, have a look at exercise 19b, question 1. And it basically gives you a scenario with a book sitting on a table and asks you to draw a diagram. What I want you to do is to practice drawing separate force diagrams for each object involved, one for the book and one for the table. Let's do that now and see what we get. So here, the book, some information in the question. We don't need to worry about the numbers, but that's just from the question in the book. But the book in the question here, will have a weight pulling it downwards, but also, because it's in contact with the table, a reaction force, a normal reaction, pushing it upwards. The table will experience a few more forces. Here's the table. And first of all, it'll have its own weight pulling it down. It'll also, because it's in contact with the book, feel the weight of the book, or rather I should say the normal reaction of the book pushing down on it. Okay, if this object is moving or accelerating, then the reaction there won't be equal to the weight of the book, but it will just be as a result of the book sitting on it. And then finally, the table will also experience the force of the reaction with the floor. So it'll experience R2, 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 and R2. I've labeled them all the same because I'm assuming that the weight is equally distributed across the table. But anyway, it's experiencing a reaction, a normal reaction force at each of the feet of the legs with the floor. And so to do this, what I really recommend, and this might sound really strange, is imagine you are the table. Okay, you're on your hands and knees, and someone is sitting on your back, or someone places a large, heavy book on your back. What forces are you experiencing? Well, you will experience the weight of the person sitting on your back. You'll also experience your own weight. And because you'll get tired, even if nothing's sitting on your back, you'll still get tired sort of holding your weight on your hands like that. And then you'll also feel the forces through your hands and through your knees. Each of those are the forces that we see in this diagram here. And so trying to imagine, if I were the table, or if I were the lift and someone was standing inside me, how would I feel? So have a go at question 1b, C and D. Try the same. Here are my answers. So pause the video, okay? But again, have a little think. So here we've got the book, we've got the weight acting down and the normal reaction acting up. For the table, this time it's a little bit different. We've got the weight of the table, the reaction from the book, but also the tension in the cable. Now maybe I could draw that better. Instead of having that tension there, it would feel a tension in that direction and a tension in that direction for the strings acting on it there and there. Have a go at the next one. Again, pause the video, the diagram. The overall diagram looks like this. Okay, and again, we've looked at something a bit like this before. We've got the weight acting down and the normal reaction pushing the person upwards. And for the lift, it will feel its own weight, the normal reaction for the person standing inside it, and also the tension from the cable pulling it up. And then here we've got a lift with a box suspended inside it. What forces will the box and the lift experience? Pause the video, have a go. And then here we've got the box the red box in the middle will experience its own weight and the tension pulling it up. And then the lift will experience the tension in the cable from this here, okay, because it's being pulled down by that cable, the lift. If you were that lift and you had something hanging inside you, okay, you'd feel the tension in that cable pulling you down, okay, as you're pulling that box up. That's an example of Newton's third law. Every force has an equal and opposite force. Every reaction has equal opposite reaction. You'd also feel the tension in the cable pulling the lift up, and you'd also feel your own weight. Okay, so get used to the habit of drawing those diagrams, those separate diagrams, one for each object, and then let's put this into practice. Here we go. So an engineer is designing a lift and needs to know the magnitude of the tension in the cable pulling the lift up. The lift needs to be able to carry a 100-kilogram person while it's still accelerating upwards at 0.2 meters per second squared. The lift weighs 300 kilograms. What's the required tension in the cable? Now, of course, if you're designing it, you would need to know that value, and then you'd probably need to over-engineer it. But you would want to know the maximum likely tension that that cable is going to experience in order to engineer it properly. There are two ways to answer this question, and we're going to do the long way first that follows that method. But there is a quicker method, and I'll show you that too. So first of all, let's draw an overall diagram. We've been looking at lifts for a while, so hopefully this comes as no surprise. Person in the left, okay. We're told that it needs to accelerate up with 0.2 meters per second squared. We've got some tension. We're going to have the weight of the lift, and we've got the weight of the person. Okay, so we're going to have also 100 G for the weight of the person and 300 G for the weight of the lift. Let's then draw two separate diagrams. Firstly, the person. Okay, they will experience their own weight, 100 G, but they will also experience the normal reaction through their feet, pushing them upwards. Okay, so that's the contact with the person on the left. They're the only two forces that we're going to this person's going to experience in this simple model. We've also then got the lift. So here, the lift is going to experience its own weight, 300 G. It's going to experience the tension in the cable pulling it up, but it's also going to feel the normal reaction of the person standing inside it. And so that is going to be R, pushing it down. And so here, this R and this R are equal and opposite because of Newton's third law. So we've drawn our overall diagram. We've drawn individual diagrams for each object, considering all the possible forces that are acting on it. We've got our acceleration going up, so we're going to choose a positive direction as upwards, because we're moving upwards, and then we're going to apply F equals ma to each object. Okay, so F equals ma, here we're going to have R is positive, 100 G is going downwards, so that's negative, equals a mass of 100, acceleration is 0.2. Now here I'm going to take G to be 10 meters per second squared. Okay. This will give us a rough estimate, and we'll have to write our answer slightly differently at the end to accommodate. So here we're going to have R equals 100 times 0.2 plus 100 G. Type that into your calculator, and we're going to get R equals 1020 newtons. Bear in mind that we have to round this to one significant figure because G is now 10, and actually all of our values are only accurate to one significant figure. So here we're going to have to say, well, this is actually just about 1,000 newtons. That's the reaction between the two people. To one significant figure. Sorry, the reaction between the lift and the person. We then can apply F equals ma to the second object, the lift. So here we're going to have upwards is T, downwards is R, downwards is 300 G, so those two are negative, equals the mass, which we know to be 300, times the acceleration, 0.2. We can rearrange to give us T equals 300 times 0.2 plus R plus 300 G, and so we're going to get T equals, now I'm going to use R, this value here, the unrounded value, because we're only going to round at the end. So we're going to get, when I substitute all that in, 4,080 newtons. And so the tension here, we have to round it to one significant figure to show that this is just an estimate. We can't claim that 4,080 is as accurate as it needs to be. Maybe it's more than that. And so the number 4,000 shows the error in our calculation. So there's a lot of calculations there, but hopefully you can see it's the same method. We just draw a diagram for the whole thing, diagram for each individual object, and then F equals ma and solve simultaneously. There is a slightly easier method. So same problem, I'm going to keep g as 10 meters per second squared. Meters per second squared. And this is a bit simpler. Now, because these two objects are really moving as if they were one, they're moving in the same direction, they're moving together, they're basically stuck together, we could just treat this as one object with a combined mass of 400 kilograms. Now, we can only do this if the two objects are connected in such a way that they're just glued together. They are the same object moving in the same direction, moving with the same acceleration, everything's the same. And so this simplifies the problem somewhat. So we've got a tension going up, and now instead of two different weights and a reaction in the middle, all we need to think about is the combined weight of 400 G, okay, newtons. They're still accelerating up with 0.2 meters per second squared, and we're going to apply F equals ma again. So we're going to get tension minus the 400 G equals 400 times 0.2, the acceleration. And we're going to get 400 times 0.2 plus 400 G. We're going to get T equals 4,080 again. Exactly the same answer, just a bit quicker. Round it to 4,000 newtons to take into account of our estimated G. Okay, 1x. So you can use this, but be careful. Don't always assume that you can always check. So have a go at this question then. Pause the video, see what you can do, and I'll reveal the answer now. Okay, and so here we have to use the two different diagrams because it asks for the reaction force. And in order to find the reaction force, we have to calculate it on each individual object. And so here we get a reaction force of 620 newtons. I've taken G in this one to be 9.8 meters per second squared. I should have said in the question. If in the exam it doesn't say what G should be, just assume it's 9.8. But if you've done it to 9.81 or just 10, you just have to round to slightly different values. That's not a problem. You still get full marks. And yes, again, here I've used R, the exact value of R in here, and then rounded only at the end. Okay. Yeah, there's nothing there. So have a look at exercise 19B. Start with question 3 onwards. Feel free then to come back to question 2. You should have already done question 1. Make sure you read through the examples in the textbook before starting. They're really helpful. Have fun.